vir vertikale projektiele. Ek gaan verseker so 'n vraag iets wees oor vertikale projektiele. You must remember that acceleration is 9,8, versnelling is 9,8 meter per sekonde kwadraat en bly konstant. Die enigste tyd wat versnelling 0 is wanneer 'n voorwerp beweeg teen sy maksimum spoed, terminal velocity, of terminale snelheid, grenssnelheid, die beter Afrikaanse woord, en dit sal slegs gebeur as daar lugweerstand is. If there's air resistance. But that would only be a theory question. So if I were to look at a vertical projectile, and this projectile was moving upwards, and as the projectile is moving upwards, obviously it slows down. Remember that the weight of the object, die voorwerp se gewig, Fg, never changes. So the weight of the object would be down. The fact that it is slowing down tells me that it's experiencing an acceleration downwards, which makes sense because Newton's second law says an object accelerates in the direction of the net force. Once that's out of your hand, if I take this pen and I throw it upwards, the minute it's out of my hand, there's no upward force acting on it. So while this thing's going up, that diagram that I've just drawn would be the free body diagram. Terwyl ek dit doen, wat is die verskil tussen 'n kragtediagram en vryliggaam? As jy die woord vry hoor, dan is die voorwerp 'n kolletjie. As jy kragte hoor, teken jy 'n krat, soos 'n boks. Krat. If you hear force, you draw the box. If you hear free body or free force, the minute the word free is in it, the object becomes a dot. Otherwise, you lose all your marks. So there's the object, there's the force acting down on the object, gravitational force. When you have to label force, listen now, when you have to label a force, you always give its name, you always give its direction, and you always say what acts on what. So the correct way to label that one would be the gravitational force of the Earth on the object, and then the direction downwards. So as jy so iets moet benoem altyd, jy sê die naam van die krag, jy sê wie oefen dit uit op wie, en dan sê jy die rigting. So, gravitasiekrag, aarde op voorwerp, afwaarts. While it's moving up, no other arrows. Silly way to remember it, but I always tell the kids, has it got wings? Can they flap? Has it got an engine? If it doesn't, then there's no other arrow. That's it. So that's its free body diagram. When it gets to the highest point, so by sy hoogste punt kom, at the highest point, its acceleration is still down. A lot of people want it to stop accelerating. It can't. The Earth can't switch off for a while just because the object's at the top. Aarde hou nie op om afwaarts af te trek nie. It's accelerating down at 9,8 meters per second squared, 9,8 meters per second squared. Free body diagram looks exactly the same, nothing changes. While it's moving down, obviously while it's moving down, it speeds up, beweeg al hoe vinniger. And in that time, the acceleration is still 9,8 and it's still down. Do you see that the acceleration, while it goes up, when it's at the top and when it comes down, is always 9,8. It's always directed down, down, and down. The reason it's directed down is because the net force is exerted by the Earth, the weight, and that acts down. If I look at the graphs for vertical projectiles, I expect basically 3 graphs. Let's do it this way. Okay, I'm going to put displacement. I shouldn't even have the delta. I could just have the y actually. Displacement, velocity and acceleration. So dit is verplasing, snelheid en versnelling grafieke. I'm going to have two sets of axes. Why am I going to do that? The two sets of axes that I'm going to have are going to be for the two options that I have with regard to direction. I could choose to draw or to consider in my calculations. Sometimes I can choose, sometimes they choose for me, a direction as positive. In the top set, I'm going to choose down as positive. In the bottom set, I'm going to choose upwards as positive. On the previous slide, I told you that acceleration due to gravity is always down, down, down. No matter what you're doing, the Earth says down. It slows you down when you go up because it's pulling you down. It pulls you down when you're at your highest point because it acts downwards. It makes you accelerate and go faster when you're coming down, down. So one of the most important things to look at is when you're looking at your acceleration time graph, to remember that if I've chosen the down is positive, it would mean with down positive, don't do that. It would mean that the acceleration for down positive would be consistently 9,8 and it's always down. Now because I've chosen down as positive, it would mean that at positive 9,8 I would have a mark, and for the whole motion, everything I do, all the acceleration will correspond to that 9,8 down. Say for example, if I represent the motion of the object, the first bit I'm going to use an object that I throw up, stops, comes down, misses my hand and goes to the ground. So as 'n voorwerp wat jy opgooi, kom bo, stop, oeps, ek vang mis, hy val tot by die grond. As ek dit kry, beteken dit vir die eerste deel het hierdie voorwerp opwaarts beweeg. While it moved up, it was accelerating down at 9,8. When it turned round and came back to my hand, it was still accelerating at 9,8. When it missed my hand and went to the ground, it was still accelerating at 9,8. Because the Earth didn't know what I was doing. All the Earth said is down 9,8. Die aarde versnel 'n voorwerp altyd af teen 9,8. If I had, on the other hand, chosen that upwards was positive, it would have meant that at negative 9,8, I would have been able to do exactly the same. I would have said, while the object goes up, it accelerates down, which is now negative 9,8. When it comes back to my hand, it accelerates down, which is negative 9,8. When it misses my hand and moves back to the ground, it comes back at down 9,8. So no matter what I do, the acceleration time graph has got to be horizontal, doesn't change its value, and it keeps the direction the whole time. Because all the Earth does is the Earth says 9,8 meters per second squared is always your acceleration, and it's always downwards. If I look at the velocity time graphs, that the slope of a VT graph always gives you acceleration. Die helling van 'n VT grafiek gee altyd versnelling. So if this acceleration is positive, as hierdie versnelling positief is, the slope must be positive. positive acceleration, positive slope. Positiewe versnelling, positiewe helling. But how does that graph then look? Remember, positive slope, think maths, looks like that. That's a positive slope. So I have no choice, my graph has to look like that. The first part means I projected the object, that's going to be the pink, upwards. Then it got to the top, and at the top it stopped. So at the top, that point is where it stopped. Then it turned round, and it came back down. And where it came back down, it eventually got to the point where it was back at my hand. The time for pink and the time for green is the same, because the time from hand to top and top to hand is equal. Now I didn't catch it, so it moved past my hand and ended up doing that. And those pieces correspond. The same thing is going to be true if I make upward positive. If I make upward positive, I remember that the object still says it can only accelerate at 9,8 down. But because I've chosen that up is positive, down must therefore be negative. But I know that the slope of the VT graph will always give me acceleration. So if slope of VT gives me acceleration, and acceleration is negative, then this has got to be a negatively sloped graph. It has to run that way. The first part is going to be where I projected it up. It reached the top. Nou draai hy om. Hy kom terug af na my toe, maar ek gaan hom misvang. So hy bereik my hand teen dieselfde spoed. That's all one ruler line. Moves past my hand and goes down until it hits the ground. And that's one line. 0. So whatever happens at the 0 is the reference. So for example, I decided that the reference was going to be the ground. Then I would know that ultimately this object hits the ground. So at the end of the orange piece, it's got to hit the ground. At the end of orange, it's got to be on the ground. At the end of orange, it's got to be on the ground. And now it's as easy as going and looking at your decision regarding direction. In the top set of graphs, I chose down as positive. Because down is positive, acceleration is positive. If acceleration is positive, I know that the shape of the parabola that I would experience, positive people smile, I'm expecting a parabola which has got a smiley. And it must end over there. But the object didn't start and end at the ground. It started somewhere, went higher, came back, and ended at the ground. So for the first part, the object started somewhere, went higher, turned around, came back, and continued to the ground. On the other hand, if it was a negative choice I had, like in the bottom example, where G was negative 9,8 in the maths class, if A is negative, the parabola looks like that. In other words, I would do exactly the same thing, and I would decide to make my parabola, but end at the ground. And I know the ground is over there. So initially, it starts somewhere, goes higher, turns around, comes back, passes my hand, and hits the ground. If we look at an acceleration time graph, and this acceleration time graph is not for a vertical motion. So it's something that I could expect in the questions where they're going to introduce momentum or Newton's second law. So it's going to be one of those questions, not going to be the vertical one. Then I would expect the following to happen. I could sometimes have a graph which gives me the set of axes for time and acceleration. So kry my asse vir versnelling en tyd en dan teken hulle iets wat so lyk en dan daarna so lyk. En dan verbind hulle daai met 'n stippellyn. The joining with the dots is just to show that there's no time that's passed somewhere in between. So if I have that acceleration time graph, and it's not vertical motion, I'll show you an example of vertical now. If that's not vertical motion, it would mean that that acceleration was, say, for example, +4, and the orange acceleration would be something like, say, -6. Usually, we would choose forward as positive. In other words, this +4 would tell me that the object was accelerating forwards and moving forwards. If you accelerate in the direction of motion, you go faster. It's moving forwards, but for the orange part, it's accelerating with the negative acceleration. In other words, it's moving slower. So this would typically be a car, where the car initially moves faster, then continues moving forwards, but moves slower. On a VT graph, that would typically be the car moves faster, and then the car moves slower. Once again, look at the slope and look at the sign of the slope. If I look at this pink slope, it's a positive slope. And that positive slope tells me why it's positive for. On the other hand, if I look at the second part, the orange part, it has a negative slope. And that negative slope corresponds to the -6. So that's moving forward. It's going faster and slower. If I were to look at this one's YT graph, it's moving in the same direction. It's accelerating. Y graphs that accelerate are always parabolas. In the first part, it's going faster. So for the first part of the slope, watch my hand. It's going faster, so small speed, small slope, faster, bigger speed, bigger slope. So it climbs. Positive acceleration, looking for the part of the smiley again. The minute it becomes negative and it decelerates for the orange part, if it decelerates, it means I'm looking at a negative acceleration, looking at a sad face parabola, and it's going to go slower. But it's still going in the same direction, so it's moving away from the time axis. It hasn't turned around yet. A bouncing object that strikes the ground, let's just imagine for ourselves what it does. If this object comes and it strikes the ground, then as a bouncing object, it means it falls down, so at the top, it's moving slowly. In fact, it was probably had a velocity of 0, bal wat van hoe losgelaat is, beweeg van hulle af. As it goes down, it moves faster. Then it strikes the ground. So as it strikes the ground at the bottom, it means it's moving at its very fastest. The next part of it would be that this ball would have to, instead of moving faster, it would have to start decelerating. Now imagine what happens when it strikes the ground. It's not instantaneously at rest. While it's in contact, if you've ever seen a slow-mo of somebody hit a tennis ball or a golf ball or somebody's nose, you sort of see squash, 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 squash. Now that's exactly what happens with a ball like this. If I have a bouncing ball, it means that the minute that it strikes the ground, while it's in contact with the ground, the first step is the ball still moves down, but it's busy squashing. So die bal beweeg nog steeds af, as jy na my hand kyk, bal tref, en dan word hy platter, 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 maar jy kan sien my hand gaan nog steeds af onder toe. And then at a certain point, it's now really as compressed and squashed as it can be. And only at that point does it come to rest. So eers as hy op sy platste gedruk is kom hy tot rus. So right at the bottom, step 2 would be that the ball stops. Then, while it's still in contact with the ground, it starts de-squashing. So it's still flat, it's still touching the ground, but now it starts puffing itself up again. It's getting round, it's getting ready to leave, but it's still in contact with the ground. So it's no longer at rest. And while it's unsquashing, it's already moving and its velocity is already changing. So die derde stap is waar hy besig is om weer rond te word. It's moving up. And if there's such a word as de-squash, good, I'm not going for orals, it's de-squashing at this stage. But it's all on the ground. The minute it leaves the ground again, it leaves the ground. So as it leaves the ground, it does so very slowly. And then as it moves away, well, not very slowly, slow. I'll come back to why it's slow now. And as it moves up, it keeps moving even slower. Until it reaches its highest point. And when it reaches the highest point, it stops. And then obviously this whole process starts again. So how would a graph for this look? Okay, let's just run through it. All the lines that run in red have a negative slope. The slope is 9,8, but it's negative. So just like in maths, the shape of the graph that I expect. Every time it touches the ground, it strikes the ground, slows down, stops, starts speeding up, and now is ready to leave the ground. So every time the strike parts, we could indicate perhaps by doing the following. We could say that is strike, that is strike. And every time we had a departure, we could say that part was depart and depart. That was leave the ground. Every time the velocity in the air is 0, it's at its highest point. Every time the velocity on the ground is 0, it's at its most squash and it's stopping. Ground pushes the object upwards, ground pushes upwards, it would mean that the acceleration, while it's on the ground, would actually be up. Up is chosen as positive, and therefore I would expect a positive acceleration. Now there are two ways to look at this. If one were to assume that the acceleration exerted by the ground was absolutely constant, then we would expect a very high acceleration because it's on the ground for a very short time. So a very big value, and we would then expect that acceleration to show as horizontal. In other words, we would want to join these bits horizontally like that. And some of the simulations that you can find where they've actually done them, it's not really a sim, it's actually practical labs that they've done, you see that horizontal bit. But it's such a small time. In most textbooks, the time or the acceleration on the ground is depicted as a point, and these lines are just joined with each other. So should you get something like that in the exam, they would accept either or. Both would be acceptable, unless they give you exactly the value and the time for which it is on the ground. If they give you the value of the acceleration and the time while it's on the ground, then choose this option. That's the better option to use. But these parts would always be the air parts. More important than that, and because of that, that's the one that they'd rather ask, is what is the shape of the velocity time graph for a bouncing ball. Velocity time graphs for a bouncing ball would look as follows. If we had the axes, kyk na die snelheidgrafieke. Daar is die asse. And now remember that YT graphs are always parabolas. So let's say for the left-hand one, I chose that down is positive, and for the left-hand one, I chose that up is positive. Let's say I chose that the ground is the reference point. So I'm going to put the ground on the horizontal line. That's normally what they do for these. It's stupid to put the ground anywhere else. If it's positive, it means I expect that my parabolas will look like that. If up is positive, it means that down, which is acceleration, is negative, and I would expect the parabolas to look like that. So let's say we start with the same one. It was in the air. Every time it's on the ground, I've got to be back on the horizontal time axis. So if it started in the air and I've got to get to the ground, it started at its point furthest from the ground. And because I'm looking at a positive parabola with an A which is positive, it means that it's starting somewhere away from the ground and moving in the form of a parabola to the ground. If you see the link between acceleration and slope, you can pick that up as well. For the first part over here, the slope is small, velocity is small. If you look over here, the slope is big, velocity is big. So it's going from small slope, big slope, small velocity, high velocity. Then it stays on the ground. It doesn't actually sink into the ground. So on the ground becomes a horizontal piece. That corresponds with the orange time just now, during which I had the velocity changing to 0 and then decreasing as it was squashing, de-squashing. And now it's got to bounce up again, but look at the shape. The maths makes these easy. If you see the maths link, it's easy. Otherwise, it's a disaster. Now I've got another parabola to put in. It's going to go to its highest point, come back, and be on the ground. Bounce again, go up to its highest point, come back, be on the ground. So every time we end up with the turning point, and that's awesome that maths uses the right word for us. Every time I get to the turning point of the parabola, it's really the turning point of the ball. That's where it turned around. Afrikaans ook, by die parabool noem ons dit 'n draaipunt. Dis exactly what hy doen, hy draai daarom. And again, red was in the air and orange was on the ground. Let's do it the other way around, and you're going to click it easily now, because remember, Down is negative. Look at the shape of a parabola I expect if A is negative. So if A is negative, I'm looking at a negative parabola, hit the ground, on the ground, do the squash on squash, bounce away, won't bounce as high because it was an inelastic collision, turn around, come back, strike the ground, stay on the ground, lift up, go up, come back, and down.